In the last few videos, we've been solving equations of this general pattern. Some constant multiple of the second derivative of y plus some constant multiple of the derivative of y plus some constant multiple of y equals 0. In this video, we're going to start talking about equations which are just one step harder, insofar as rather than having 0 on the right-hand side, we have some function f of x. Now, the main thing that makes this a bit harder is that we can no longer add and multiply solutions together to get other solutions. But we can do something of the sort. Let's see what happens if we have two solutions and we subtract them. So suppose we have two solutions, y1 and y2, to this differential equation. Now, consider what happens when we take y1 minus y2 and stick it into the left-hand side of this differential equation. So a times the second derivative of y1 minus y2 plus b times the derivative of y1 minus y2 plus c times simply y1 minus y2. Well, the terms involving y1 are all equal to something that looks like the left-hand side of this, and I promised you this was a solution, so this is equal to f of x. Similarly, the terms involving y2 also make up a solution to this differential equation, so we get minus f of x. But that's 0. So whenever we have two solutions, then their difference, y1 minus y2, is a solution to the homogeneous equation, which is an equation of the sort we were considering recently. We can turn this to our advantage. Let me show you how. Suppose we have a solution to the same equation Suppose we have a solution to the differential equation a times second derivative plus b times first derivative plus c times y is f of x. And then suppose we can also solve the homogeneous version of the equation. So we have a function z such that a times the second derivative of z plus b times the derivative of z plus cz is 0. So we have a solution to the equation we're interested in, and suppose we also have a solution to the same differential equation, but where we replace the right-hand side with 0. Then if we add y and z, and look at what that satisfies, so we take the same process, a times the second derivative plus b times the first derivative plus c times the function, and apply it to y plus z. Well, the terms involving y are ad squared y by a times the second derivative of y plus b times the derivative of y plus c times y, and the terms involving z are a times the second derivative of z plus b times the derivative of z plus c times z. So what we get is f of x plus 0, which is of course f of x. So that means if we have just one solution to this differential equation, we can make a whole family of solutions by adding on solutions to the corresponding homogeneous equation. So we just take one solution of this, and then we can build many other solutions by adding on solutions to this, and the resulting thing will still be a solution to this. This happens so frequently that we give names to this process. We call y the particular integral Integral is an old-fashioned name for a solution of a differential equation. After all, as we said at the beginning of this series of videos, integrating really is solving a differential equation. And then the thing we add on to get another solution is called the complementary function. So in this language, we get the general solution to this differential equation by finding just one solution, the particular integral, and adding on solutions to the homogeneous version, the complementary function. So the general solution is the particular integral plus the complementary functions. Let's work through an example. Let's consider the differential equation d squared y by dx squared minus y equals 4x. So we can do the bits in either order. We could find the particular integral first, or we could find the complementary function first. Let's start by finding the particular integral. So what would satisfy d squared y by dx squared minus y equals 4x? The sad news is there's no general way of finding a particular integral. In order to find a solution, you just have to guess. Usually, guessing things that look a bit like the right-hand side is not a bad idea. If, in fact, we took y to be 4x, then the second derivative would vanish, because differentiating 4x twice sends it to 0, and we get minus 4x here. So we'd have the second derivative of 4x minus 4x would be minus 4x, which is not quite what we want. But if we take y equals minus 4x, we get a solution, because then d2y by dx squared equals the second derivative of minus 4x, which is 0, and so second derivative minus y is minus 4x, which is 4x. So that's the particular integral that we're going to use. In order to find a general solution, we've got to work out the complementary function so that we can add it on. So we now solve so to find the complementary function, we solve d2y minus dx squared minus y equals 0. Of course, we've done that one before when we form the quadratic equation that tells us what exponential we should guess. So we guess an exponential. The corresponding quadratic equation is k squared coming from this term minus 1 coming from this term equal to 0. So k is plus or minus 1. The roots of this quadratic equation are at plus 1 and minus 1. And therefore the complementary function is y equals a e to the x plus b e to the minus x. So now we put the two together, we find the general solution by taking our particular integral and adding on the complementary function. So the general solution is y equals a e to the x plus b e to the minus x minus 4x. Finding the particular integral isn't always that easy, but we'll do a lot more examples in the next few videos.